Okay, so I'm going to try to give you guys a little hint on this problem that I keep asking you to do. So the claim here is the idea that dimension is well-defined. So what do I mean by well-defined? Do you guys know what this word means? Well-defined?
It's like, this is the definition, there's no arguing around it.
Yeah, well-defined means kind of that it's unambiguous, right? So in this case, I would be concerned because I defined dimension as the number of things in a basis, right? And if a basis could have different numbers of things in it, then dimension wouldn't be well-defined by that trait. Does that make sense? So here's the hint, right? Let me consider a basis for... Actually, let me consider a couple sets in R3, or in R2. So I'm just going to kind of peg myself in R2, and this is just hint of trying to figure out what's going on, right? So in R2, I think I have a standard basis that I know, which is, I guess I should write that in the usual order instead of the backwards random order I just started with. This is a linear independent spanning set for R2, right? So I and J, right, is a basis for R2, yes? Okay. Let me construct another spanning set, and then see if we can figure out why linear independence is necessarily broken. You guys with me on that? So I'm going to say, all right, let me consider another set. I'm going to consider 1, 2, 2, 1, and 1, 3. Now, I assume you guys can look at this and see that this isn't...
Yeah, it's a combination of the other two.
Yeah, like, pretty clearly, there's some linear combination of these first two that would get me the third one.
Mm-hmm.
How do I know that?
Well, there are 3 vectors on 2, so...
Yeah, you're kind of intuitively using the concept of dimension, right, if you're going that way. Another way I could look at this is I could just be like, okay, look, there's 2 vectors, they point in different directions, and so I'm going to necessarily be able to get a hold of this third one.
Mm-hmm.
So let me kind of write down what we were working with in order to try to see if we can motivate a proof that these should always have the same number of things, right? So I'm going to kind of pretend that this is my set of vectors V, and this is my set of vectors W. And in this case, R2 is my overlying kind of vector space. You guys see that? So I've got my vectors, I'm going to call these V1 and V2 here. They're I and J, right? And then I'm going to write my vectors W1, W2, and W3 here. Okay, and I know that V is a linear independent spanning set because it's a basis. You see that? So I'm assuming that I have V, which is linearly independent and spanning. Good with that? Okay. Now, I'm going to consider W, which is a set of vectors that is spanning and has at least one more vector than V did. Good with me on that? Okay, so now my goal is going to be to consider I'm going to consider a sum of these things. You guys see that? So I'm going to multiply these by some coefficients. What did I call them last time?
I think B1 would be
That I think was what I called... Yeah, it doesn't matter. So coefficients-wise, I'm just going to consider a sum x1 w1 plus x2 w2 plus x3 w3. Right? I'm going to set this equal to 0. And now, my thought is, look, because these are spanning, but there's more of them than there were in a different spanning linear independent set, these ones probably are linearly dependent, right? So I should be able to find x1, x2, and x3 that aren't all 0, so that this sum actually works. You guys see that? So the way I'm going to do that is I'm going to say, okay, look, V was a spanning set, right? So I'm going to rewrite the W's in terms of the V's. And I've given myself some explicit numbers here so I can show you which things are known and which things aren't. You guys see that? So over here I'm going to consider, I'm going to write my W1s, right? So my vector W1 is going to be A11V1 plus A12V2. You see this? So my A's are going to be which W am I making, comma, which V am I using. You guys see that? In this case, with my kind of motivating example, I know what those two numbers are. You guys see that? In my motivating example here, I should be able to say explicitly that A11 is what? 1? You guys see it?
That's 1.
So W1 is 1 times the vector 1, 0, plus 2 times the vector 0, 1. You guys see that?
Yes.
So it's clutch to realize that when I rewrite the W's, I'm going to know all of the A's. You guys see that? All the A's are going to be known to me. So I'm going to do this quick for the other two. So W2 is going to be A21 V1 plus A22 V2. And in this case, what are those coefficients? 2 and 1? Perfect. You guys with me? So again, I know the A's. W3 is going to be A31 V1 plus A32 V2. And that is going to be, in this case, 1 times 1, 0 plus 3 times 0, 1. You guys see that? Now I'm going to put I'm going to put these, right, my W's, into my equation here, right, the thing I'm considering. You guys see that? So, we're going to say that we've got x1 times, and here I'm going to have
1, 2.
my A11 V1 plus A12 V2, right? And in my specific example, I'm going to have 1 times 1, 0 plus 2 times
0, 1.
0, 1. You see that?
Yeah.
Plus x2 times
2, 1, 0.
W2.
Yeah, exactly. Times W2. And W2 is 2 times 1, 0 plus 1 times 0, 1 plus x3, right?
1, 0 plus.
Stuff is going to be the 0 vector, right?
Yeah.
Yeah.
You guys see that? So then my question is, I'm trying to what? What am I trying to do here?
Solve for x1, x2, x3, such that it's 0.
Good. I'm trying to solve for my x's, right?
Yes.
You guys see that?
Yes.
How many equations am I going to have?
3. Oh, you only have 1, 3.
Yeah, well, you could set each one equals.
Yeah, so it feels like I have one long equation, right?
Yeah.
There are 2 equations there.
Oh, because you separate
Right,
the
one for V1 and one for V2, and because
Yeah.
they're linearly independent, the coefficients have to add up, have to be 0, right? Okay, see that? So if I combine the coefficients on V1 and the coefficients on V2, so if I rewrite this, right? So I'm rewriting as x1 times, and this is going to be a11 times v1, right? And in my case, it's going to be x1 times 1, 0. And then I'm going to have 2x1 times 0, 1. That's really going to be x1 times, which a is this guy?
A12.
Good. It's A12. You guys see that? And then I'm going to have plus, and I'll have some stuff for x2. I'll have x2s, right? So I'll have 2x2 v1 plus 1x2 v2. And then I'll have x3 times v1 plus 3x3 times v2. Oops. And this is all still supposed to be the 0 vector, right?
Yes.
And now if I group these according to which v they're attached to, those are my v1s, right?
Yes.
And so in order for this linear combination to equal the 0 vector, because the vectors I started with are linearly independent, right? I'm going to get an equation. That's going to be that the coefficient has to be 0. You guys see that?
Yes.
So the coefficient there is going to be, out of the squiggles, I'm getting x1 plus 2x2 plus x3 has to equal 0. You guys see that? Yeah, so if you're going to want to track that back, right? In order to get a general proof, you're going to have to track it back, and you're going to have to put in the appropriate A's. But you can do it, right? They're all there, and the A's are known. Don't get confused by the bastards. They're just a number you're going to know. You see that? They aren't something you're solving for. Then in my second equation, right? So for V2, right?
That's 2.
I'm going to get 2x1 plus 1x2 plus 3x3 is 0.
Yes.
It's with me? Okay, now, notice,
You've got 3 unknowns and 2 equations.
perfect. That's what I was hoping to see the other time when I was pointing at that thing. It's like, look right here. There's equations because of linear independence, right? And the thing about it is it got lost in all the symbols, right? So the kick is here, right? You're going to end up with as many variables as you have things in W, and you're going to end up with as many equations as you have things in V. And if they're not the same, then you're going to have a problem, right? And so I'm going to start with the small one. Like, without loss of generality, start with the small one. Assume that's the real basis, right?
Yeah.
Then the big one is going to have at least one extra variable compared to the number of equations you're going to have. And then you're going to be able to say, bruh, there are infinitely many solutions to this, so pick one. You guys see that? That's the weird thing here. What are you barking at?
She's seen ghosts.
She looks straight at me.
She doesn't like persons.
Racist.
I
No,
think,
no.
I'm
Like
this.
father, like daughter.
I, s- I-
This
I
is
s-
all on a recording.
I swear I went like this.
That's cool.
Rashida, can you please tell people I'm not racist?
Hear all that.
He's not racist.
That didn't sound like a ringing endorsement. I'm gonna have to cut this video out.
Yeah.
Thank you,
If you
Logan.
need help, blink twice.
yeah.
You need help, please. What is it? Hold your hand out or something?
Yeah.
Anyway, so what's weird here, right, is that there isn't one answer to this. There are necessarily infinitely many choices for non-zero coefficients, which is real weird because you're used to you're used to looking for something and then finding one of it, right? And in this case, there are necessarily infinitely many because you could take this whole equation and multiply it through by whatever you wanted. See that? So you guys hopefully write down a proof for me next time, generally.
We'll try.
Cool.